Okay, so last week we ended on binary trees. Or actually, we ended on binary search trees, which is a special case of a binary tree. And so what's the constraint with binary search trees over binary trees? What are the two rules that you need to follow?
Anything less than or less? Anything greater than or less than, right?
Mm-hmm. Or you can say it again if you didn't hear.
Sorry, a what tree?
A binary search tree? So there's
Over what?
over a binary tree. So, well, first, what is a binary tree?
Wasn't it that we had to have like maybe this was a different concept that we had to have the whole layer filled out, or like it was said to be like the
I think, well, that's talking about the structure of a tree, and then we had a few terms for that. We had complete, full, and then also with regards to height. This is not quite that.
Okay.
So a binary tree is just what?
It's in binary tree is just everything just in a tree formation.
Well, I mean, when you see hear the word binary, what does that imply about that formation?
Yes or no? One or zero. Like two things.
Two things, but what does that imply about the actual structure of the tree? If you only have two, if I'm a node within this tree, what does binary mean? Yeah, I only have two children, right? So that's binary tree. Now a binary search tree is just a binary tree with two additional constraints, which are. Well, that implies order, but it's actually a little harder to state than just order.
Less than on one side and greater than on the other.
Yeah, and so let's suppose we choose well, it depends on the convention we choose. Hey, Jamie. In terms of which way we traverse first, and for us, we're adopting going left first, right? That's for our traversals, we traverse left and right. And so if we're traversing left first, what does that say about what I'm talking about in terms of this order that Ari presented to us?
That everything on the left is less than your root, and everything on the right is greater than.
Yes. Okay, so that's a binary search tree. That's a definition. If anyone asks you, that's the way you would answer it. Okay. And so here it is. This is pretty much just a little more formal definition. Anything that is less than a particular node will always be in its left subtree. Anything greater is in the right. Okay? Straightforward? Any questions on this? Okay. So, and we went through this. This is just review. And so we know there's a few operations we can do on it. We'll talk about most of these. And so let's get started. And so, well, let's go back. I want to look at this. So if I wanted to search this binary search tree, and if we know we only started at the root, right? That's always where we start for any node-like structure, at the top. For linked list, we start at the head, and for trees, it's the root. And so if I wanted to search for, say, Tom, what would be the steps to do that? How would I know to get to Tom from Larry?
Check if it's greater than or less than.
Yeah, so is Tom greater than or less than Larry?
Greater.
Greater, and so I go where? You're right. Well, I mean, the first thing I should ask is whether or not Larry is Tom, right? And so the answer is no, and now I can decide which way to go. And so I'm now here, and so I ask, is Rhonda Tom? No. And so now I ask the question whether or not it's less than or greater than. Tom happens to be what relative to Rhonda? Tom? TRST greater. And so that's right. That tells us which way to go.
Right.
You're right. Boom. Is Tom equal to Tom? Yes. Were you gonna say no? So yes, Tom is equal to Tom. Well, you might have been right if Tom was lowercase in one case.
That's true.
And so that we found Tom using a particular type of search, and that ends up being the algorithm. And so going back to this slide, so we know for the searching that we want to find a particular node value v, and we return true or false determining on whether or not that particular value is within the tree itself. And so we start at the root node as always, and we keep on going until we reach the null pointer. And so we ask ourselves, is v the thing we're looking for? If it is, we found it. Otherwise, we decide which way to go. Now, if we go all the way down to the null pointer, so if I'm looking for Tom in this tree, this is not Tom. Tom is greater than Larry, I go right. This is not Tom. Tom is not Rhonda, so I go right. But then what happens when I go right?
There's no.
Yeah, so if I try to go right, I see it's a null pointer. And so what happens when I reach a null pointer?
You go back to your return false.
Well, yeah, return false, but why? Because it's not in the tree. Right? Remember, the goal is to try to find Tom.
Oh, okay.
If we get all the way down here without finding Tom, that means Tom was never in the tree in the first place.
Yeah, you're right.
Okay, makes sense. Okay, so that's binary search. Let's go through a couple examples. So if we search for Gary, boom, we start at the root. V is, well, Gary's not the same as Larry, despite the fact that they rhyme. And so no. We know that if we remember our alphabet, Gary is less than Larry, so we go left. Boom. We go back to the top of the loop. For this particular node, Fran. Is Fran equal to Gary? Nope. And so is Gary less than Fran? No. F, E, F, G. And so is it greater than Fran? And so we go right.
Is it possible to have Rhonda under Fran in the right?
No, not based on the rules of, wait, so Gary.
Barry and Rhonda.
Wait, say that again.
Barry and Rhonda?
Barry and Rhonda?
Yeah.
Oh, yeah. So, well, no, because Rhonda is greater than Larry.
Yeah.
Right.
What happens if they're equal?
They're equal. So this is, by definition, this binary search tree has no duplicates. Right. So, what do you mean? What two things are equal? The thing we're searching for, or two nodes?
The first one could be if there's two Frans, but then the second one would be if you arrange the letters in such a way that.
Oh, well, so in terms of the nodes that are currently in the tree, you'll never have duplicates. That's just not the way we define this tree. Right, so binary search trees do not have any duplications within them.
Even so, just because we were using the characters and we're taking like their ASCII values and adding them up, that would be like if it's less than or equal to, right?
Kind of, you don't add up the ASCII characters, but I kind of get what you're saying. I mean, we're comparing ASCII characters, that's what we're doing, but we're not adding anything up.
Oh, okay. I was thinking value and that one was like, because you could maybe make another word that.
Oh, yeah, actually, keep that in mind, because we'll see that idea again. But no, when we're comparing strings, we're not adding these letters together, we're comparing letter by letter.
Okay.
The way we would in terms of just, reading a paper.
Okay.
But on top of that, for binary search trees, there are no duplicates, right? I mean, you can implement it such that it has duplications, it's just, it affects some other things that we'll talk later on. But for now, for the way we define this binary search tree, it is completely unique in the values that it stores, okay? Okay, we sort of there was an initial question that I initiated at Cascade, and so, was it your question, Jimmy?
Oh, about Rhonda being under Fran?
Well, so in this case, Rhonda cannot be below Larry. So you cannot move Rhonda
Left.
into the left subtree of Larry, right? If Larry is the root node, this must be on the right side of Larry.
Okay.
But that isn't to say that we can't rearrange this. Like I could make Fran the node, in which case everything sort of like tilts up,
Yeah.
right? I could do that, but again, relative to each other, Rhonda cannot go less than Larry. So she must remain here if Larry remains here. Gary and Fran. So, well, no, because Fran is less than Gary, right? So if Gary went here, F is on the right subtree. So in that case, no. Yeah. I mean, there are ways to do it. You could rearrange this, but what was suggested so far was not valid binary search trees. We'll see more examples. Okay, so anyways, that's that. Let me go through this. We already have, and so for this binary search tree, let's spend a little more time searching for a couple more people. And so, for example, Kang. And so we start at Mel. Kang is not Mel. And so where do we go? So K is what relative to M? Less than? Darren, not Kang. K, A, B, C, D.
Oh, yeah,
So,
right.
right. Is John Kang?
No.
No. Was a J.
K.
Which A, left or right? J, K.
Left to the left.
Wait, no, but Kang is greater than John. J, K. I mean, you said it right, it's just you interpreted it wrong. So J is before Kang. That means Kang is after John. J, K. Right. So, J, K. Lol. Okay, and so we go right, what happens? No pointer, so that means what? I'm sorry?
Return false?
Return false, but just in terms of just the problem itself, Kang is not in the tree.
Not created.
Yeah, Not there. Kang's missing. MIA. And then we could do the rest for Dale and Sam, but you guys get it, right? Do you guys want to go through another example here? Okay, so you guys get it. Once you get the alphabet, I think you get it, right? Okay, and so here's two implementations. One is iterative, one is recursive. Can anyone tell me which one's which? Which one's recursive? The left, how do you know?
Because you're calling the function again?
Yeah, I'm calling myself again. All right, so boom, boom, and there's some base cases here as well. And so there it is. I mean, this is pretty much a direct translation of what we saw in the previous slides, right? This iterative version. Here's a recursive version. And for the project, you're implementing a binary search tree in which you do it recursively. So maybe the slide might be relevant for that project. It might actually give you the answer. Okay, so here is the recursive binary search tree, and we'll step through this so we can understand it. Okay, so I have a main here. I define a Boolean in which I believe this will represent whether or not I found a particular node within this tree. And right now, it looks like I'm searching for the value 14, and I'm passing in the first node in which I'm searching. Okay, and so bool find, we create that memories from somewhere. We just have it. Okay, so we call search, we pass in 14 for V, and the address of whatever the root node is. Boom. And so is p root null? No, I mean, I don't draw it, but it is pointing to a node, right? And so this has an address. I'm just not putting the numbers up there because I'm assuming at this point you guys get the whole address scheme, right? But if not, when you're doing it on your own, go ahead and fill in some fake addresses and walk through it. Okay, and so is 14 the same as my current value?
Nope.
No, because I'm currently pointing at 13, or the value within the node that has 13. And so I need to, so I ask myself, is 14 less than 13? No. It's a bit easier, isn't it? I think so. This is not letters, so I have a hard time with alphabet too. And so since it's not less than, well, since it's greater than this, we don't go to my left. Rather, I go to this else block, which has me search my right. Okay, so I recurse on my right subtree. Boom. And so let's create that function call. I'm passing into that tree with the value 7, or I'm looking for 14 still. Is 14 17? No. Is 14 less than 17? Okay, and so I go ahead and go left. And so pass in the left subtree, look for 14. And one more time. This is clearly not null, and so we go down to this if statement, is, and then Ebony, or Breezy said it quietly. And so in people in the back, what does this evaluate to? Anyone? Is this true? For those who are paying attention, I suppose? Yeah, it returns true, right? Because we're looking for 14, and currently this is 14, and so boom, we return true, so we're done. And then we jump all the way up to this recursive call, then we jump up to this recursive call, which goes up to this recursive call, which would go to main, we store this into bfind, and we can do whatever we want to do with that. Okay, so that was stepping through a recursive search on a binary search tree. You might want to know this, if not for this class, but for your interviews as well. So, in average, a binary search tree with n values, how many steps are required to find a node? So what is the big O of search? That's the question. Well, let's step through it. All right. So here's our tree.
You're cutting them up.
Well, possibly. Let's step through this, and we'll see if whether or not your assertion is correct. So we start at the node, and so when we go down here, do we have to consider this at all?
No.
No. And so effectively, what did we do in terms of the problem space? By going to the left subtree, we no longer have to consider the right subtree. So the problem was cut in half.
Oh, it is log-based too, yeah.
Yeah, so,
Yeah,
I mean,
so
you
I'm
guys see it right now. So if it's not this node, we go down either to left or right.
Yeah,
And so we no longer have to consider the right subtree. I just cut the problem in half. And so can people see? I mean, you mentioned it, but for those who might not have heard, what do you guys think the big O of binary search is? And this will be a test question, you can guarantee it. Yeah, log 2n. Because we're cutting the problem in half each time, right? You guys see that? Okay, so boom, 50%, 50%. Boom, 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 and so on. So log base 2n, super fast. Well, not as fast as constant time, but pretty good. And if you don't know what that means, you might want to get to the point where you do. Yeah, constant time. Well, constant time means it just does not depend on the size of the problem, right? So regardless of how big the problem is, constant time means I get it within some number of steps, independent to that size. Okay, and so in the worst case, with a tree that has n values, how many steps will we need? In the worst case, this was assuming on average if the tree was a certain way. Now we're considering a tree that is looking a different way, has a different structure to it, that would result in a worst case.
Log base 2n squared.
Well, log 2n is the average case. That's what we just saw in terms of cutting it in half.
When the tree is horizontal, not even like only have like.
Yes, but then you're gonna say something after always. Or maybe you're just gonna stop at always. So it's not. No, it's not. Well, always what would be the question?
You always divide it in half.
Well, that's the algorithm. We will always divide in half if we can divide in half. That's if we had a tree like that. If we had a tree that looked like this. This is a nice looking tree. I don't know about you, but I fancy this tree. Now, okay, so what else could a tree look like? That a straight line. If I had everyone in my left subtree, right, and so there's no way of going right, so I always have to go left.
Okay, so it'd be n.
Yeah, it'd be n in that case. Okay?
But it wouldn't be ever greater than n.
No, I mean you would hope not. That'd be a pretty bad searching algorithm if it was. So yeah, because it would imply that you would visited more nodes than there were in a tree to visit. So, so yeah, n. And again, if I'm going too fast, let me know. Again, I'm just assuming, that you guys get it. So yeah, if it looks like this, it's gonna be n. Let me see something real quick. Okay, so if there are 4 billion nodes in a binary search tree, how many steps will it take to search this tree if it was a nice tree? So divide 4 billion in half some number of times. How many times did you divide in half? Well, it ends up being 32. Yeah, 32 steps to search 1 billion nodes. That's pretty good. That is very good. That is very good. That's why we use binary search.
But for binary search, wouldn't every value you're searching for have to be unique?
I mean, the idea of binary search. Well, I guess I'm not sure your question. So,
Well, it's just like you said, you can't have 2 nodes with the same.
well, no.
value.
So a binary search tree is unique, and so
Okay.
yes. So the search on a binary search tree will be unique, but how would that affect this 32 from 1 billion? Unless you're addressing something else.
You're addressing. I got it right now. You're addressing the algorithm, and I guess I was talking about the tree itself.
Well, yeah, the tree. Well, the algorithm operates on a tree, and the tree, by the way we define it, has no duplicate values in it. Now, you might be thinking about a broader problem. Like I could have an array, right? An array that's sorted in some way, and I can do binary search on that array. Now, that array, if you define the problem as such, you could have duplications. That's just the way you would define that array, and you could still do binary search.
Okay.
But that's that problem. This problem is we have a tree that's unique. in
Yeah,
values.
I get you.
Okay, so yeah, pretty pimp. Okay, so that was searching. Let's talk about insertion. Although, are there any questions on searching? You guys get it? Pretty big deal. You will see this on everything, in your cereal, in your pasta, in your job interviews. Okay, and so let's go ahead and talk about how we actually go about putting something within the tree itself. And so, where would I put Carly? Well, okay, so this is pretty clear. We go left, left,
Right.
car, A-R-E. Yeah, so E and L, right? So right now.
Left.
Yeah, so here?
Yeah.
Yes. I think I agree with that, but I'm not really good with the alphabet. So yeah, right, or left. What about Ken? Who is not here right now, which makes me a little sad.
Probably JK, right of John.
Right of John? Yeah, JK, because we talked about it. So yeah, so right of John. You'll never forget the order of JK from now on. So, what about Alice? Well,
Right under.
Straight down.
yeah, Arissa. So L is less than R, and so boom. Okay, and so that was insertion, and so the question is, how do we program this, or how do we formulate the steps that we did subconsciously in our brain into steps in which a computer can follow? And so, well, first of all, we need to indicate the problem, or phrase it in such a way that we understand it. The input is a value to insert into the tree, and so if the tree is empty, what do we do? I mean, even with like looking at the slide, if I want to insert Alice in an empty tree, what do I do? Yeah, just make a node and put Alice there, right, as the root node. That makes sense. Same thing with the linked list, right? If I had an empty list, insert a node, insert it at the beginning. Okay, and so suppose the tree is not empty, and so we start at the root, and then we do some looping, but what questions do we ask?
If it's bigger than or less than something, and then when it's not equal.
Yeah, I mean, I think that collapses.
You have to move things over.
Well, I mean, be careful. We're not actually doing any moving here. Not yet. Well, we go until we reach a null pointer. And so that's part of it. Let's put all these pieces together, because I think you all phrased it. We just need to put it in order. And so if it's equal to the current value node, we do nothing, because unique, right? Unique tree. Okay. If it's less than, what was that?
No, I was just reminding myself. I forgot to eat.
I don't have any food.
No, it's cool, dude.
I ate my banana already, so I can't help you. So if it's less than the current node's value, if there is a left child, then we go left. Otherwise, there is no left child, and so we just do what? Without even reading this. If we know it goes to the left and there's nothing there, what can we do? Just put it there. Yeah. And so that involves creating a new node, putting the value in the node, having its left and right child point to null, and so on. You guys can conceptualize this, right? If not, let me know, because I'm assuming that you can. Otherwise, if it doesn't go left, we know we go right, and everything else is the same. If there's a right child, we simply go right again to make that comparison there. Otherwise, we just simply put this V into a new node that will reside within that right position of that particular node.
Sorry, if V is equal, why would we be done? We can't have duplicates?
Because we can't have duplicates.
Okay, so it's already there, so you don't need to do it.
Correct.
Okay.
Again, that's just the way we're defining our binary search tree. You could create another another type of binary search tree in which you allow duplicates, although there's a smarter way of doing it rather than inserting a node into the tree. You tell me, what do you think? Instead of inserting a whole new node,
You just add the counter.
yeah, just have a counter keeping track of the number of times this node appears within a tree itself. Okay, and so here is a definition for a node itself. We have a constructor, although you don't really need it. We know that minimally we need to have the thing representing the value, and then node pointers that tell us who the left and right child are. No food and no sleep? Man, what are you doing?
Black Friday.
Black Friday? Oh, did you buy anything cool? Buy me a webcam. This one's not very good. Anyways, oh, actually don't. You can't buy me anything. That's conflict of interest. Yeah, I'll get fired. Oh, we can't even talk about this. So, okay, let's talk about the search. Moving on. So here is a rough class or an object, a binary search tree object, where I have my constructor just sets my root to null. Of course, this just means create an empty tree. Right? Again, this should be null pointer if you're using anything after 2011. And so we want to define this insert function into our private member variable root. And so let's go ahead and go through this. There we go. And so, I mean, this looks kind of ugly, but this is pretty much a translation of what we saw in the previous slide. Right, we'll walk through it in a second. Is this recursive?
No, not really.
Not really. Is this well, let me think. It's kind of subjective. Beauty is in the eye of the beholder. But would you, if you would compare this to perhaps a good-looking function, would you consider this a good-looking function? No. Yeah, I agree. It's kind of ugly, right? It's kind of. Well, I mean, it's just hard to read, right? And so, and this is being done iteratively. And so, what do you think? Do you think the recursive version would that look nicer? Do you think?
Yeah.
Probably, and it does, and that's what you'll be implementing. And in general, for again, if we talk about the tree, we can recognize that the left subtree looks like the entire tree itself, right? And the right subtree looks like the entire tree itself. And so there's this idea of self-similarity between the sub-problem and the entire problem itself. When you have that situation, it might be that you want to use recursion, if not for the only reason then to have it look nice, right? Because this isn't particularly nice to look at. But it is what it is. Let's talk about it. So if the root node is null, we just simply add the node there, right? Otherwise, we do other things. And so we're going to create a cur pointer pointing to our root. And so we're going to loop continuously. All right, and so essentially, this is just going to be traversing through the tree. And so if the value is the same as the current node, we just do nothing. Otherwise, we just ask if the value is less than the current value. If it is, we ask if there's nothing to the left of our current node. If there's nothing there, then we simply have current equal cur left. We might do something with this later on. But no, we just simply, no, this is traversing to the next node, I'm sorry. All right, because this is not null. I thought this said if this is null, but it says if this is not null, then we just traverse left. Okay, is that clear? A little trip up over on my part, but do you guys understand it? For those who are paying attention. It's okay if you're not. I tend to zone out for these things as well. And so otherwise, that means it is, I'm sorry. And so that means it is null if we reach this part. And so we just create a new node at that point, right?
Okay.
With a new value. And then we're done. And otherwise, we do the same thing for the right subtree. Okay, so this is pretty much a word-for-word translation of the slide with the algorithm.
Wait, so in general terms, you use recursion whenever you copy the same code over?
I mean, I like the first part of that statement, or that question. You can always use recursion in place of iteration and vice versa. The two can be swapped. Now, whether or not it results in nice-looking code depends on the problem itself. And my assertion to you is that if the problem has this self-similarity aspect to it, then recursion, the code that you create using recursion will likely look better.
Okay.
But you can always swap one or the other. Although in some cases you don't want to do it. Like, well, I mean, this is iterative and it's not very nice looking, right?
Mm-hmm.
Okay, but you guys get this. I mean, if you get the algorithm, you get this, because this is just a straight-up translation between that last slide. And so you might need to know how to insert something within a tree, presumably soon. If not the assignment, then the final. And so, bless you. So if I create a binary search tree, it starts out as null. If I insert Larry, what happens? What happens?
You make a new node.
Yeah, because the tree is empty, right?
Yeah.
So boom, make a new node and throw Larry in there. Boom. And that's how you draw that. And then ... we might do a few other things. Suppose this is our tree now. If I decide to insert Phil, well, where should it go?
To the right
To the right
of Larry.
of Larry, but then where to Rhonda, or from Rhonda? Yeah, to the left, because P, Q, R. So boom. But if we want to traverse the code itself, So we have a current node, a current pointer pointing to the node with Larry. We go through this looping process. Phil is not Larry, so we don't enter here. Phil is not less than Larry, and so we don't enter that if statement. Phil is greater than Larry, and so we enter this. Now, if the right is not null, which it is or isn't, is not, and so we do what? What's cur equal? Yeah, so this pretty much just means move to the right, but we have this equal the address of Rhonda's right child. Wait, Rhonda or Larry's? Larry, sorry, I stepped ahead. So boom, and now what happens? Well, this matches up with the for loop. Yeah, we go back to the top. We do this whole process again, but with Rhonda, right? Is Phil Rhonda? No.
Nope.
Is Phil less than Rhonda? I am hearing conflicting answers. But I heard 2 yeses to 1 no, and so the majority wins. And so Phil is less than Rhonda. And so we go through the process where we ask, well, is Rhonda's left child null? Yes, and you just look at the picture. And so that means we don't traverse any further. We simply do what? Add any node in which Phil resides. Oh, well, right now, so this assignment here. So this points to Rhonda.
Oh.
Her left is assigned the address of this new node. I just put it into 1 line. If you want to break up in 2 lines, that's fine.
Wait, so that's bad code. Do not code that?
No, it's not bad code, it's just ugly code.
Okay, so I'm not gonna code that.
Okay. Yeah, I mean, just do it recursively.
Oh,
Right.
pretty.
Do it recursively. Well, I mean, I say that. I mean, yes, recursive function will make this look prettier, but what do you sacrifice when you use recursion?
It's not as easy to look at it and understand it.
Well, you have
Well,
exceptions.
maybe. I would argue the other way. I think recursion is easier to understand for the problems in which it applies well.
Well, you have exceptions?
I mean, that's true for iterations as well. I mean, well, the question is, what sort of exceptions are you talking about then? If you want to go that route, but generally speaking, I don't think you're. Well, so let me ask you this: is memory bounded when you're using recursion? No. You almost said yes. Well, you did say yes, but then my question is why yes? Because every time I call a recursive function, I need a new memory new memory space for that function
Know
call.
how big
Yeah.
the tree is.
I don't know how big this tree is, and so if I have to recurse 1,000 times, I have to create 1,000 function calls. How many function calls happen here? 1. Right, and so this uses less memory than recursion. That's always going to be the case.
Just buy more memory.
Well, what if you're doing it on your iPhone? Right.
The iPhone is okay.
Buy a new phone.
Yeah, buy a new phone.
What about your iPhone? Is it a complaint about Apple? I'll listen to it.
I said, why have an iPhone in the first place?
Ah, that's even a better statement. I like it. It's all right. Nothing wrong with Macintosh. Okay, and so,
There's a lot of things wrong.
anyways, no, this is almost as bad as getting to like political discussions. And so, because there's, I mean, there might be a couple fanboys in here, fangirls. So,
Dude, I have a MacBook Pro and it's pretty bad.
I don't know. People are pretty passionate about these other things. So, anyways, I'm sorry, I'm getting distracted. And so, as with binary search, there's a recursive version. In fact, you have to figure it out for the project itself. And so given a random array of numbers, if you insert them into a binary search tree, what would the binary search tree look like? This is an excellent interview question. And possibly final question. Every now and then, I'm just gonna shout the word final just to get people's attention. So given a random array of numbers, if I went through that array and started inserting into our binary search tree, what would be the structure of this binary search tree? If I gave you a random set of numbers, and we picked a number, insert it into a binary search tree, that creates a node. And we do this, and so we're creating nodes within that tree. What would the tree look like?
Like
What do you mean by regular tree?
It has your root.
Well, okay, it has a
Your
root.
root would be the first number that you grab out of there.
Okay, sure.
You grab the second one and you.
That goes someplace,
Yeah.
left or right, sure.
Oh, it could look really weird.
Well, I mean, if it's completely random.
One for your first number and then everything else.
Well, no. So you're trying to think of specifics from a expected value. You can't do that. So just on average, so just a bunch of random numbers. I throw it into a tree. What does it look like?
Binary tree.
Well, it's a whole. Everything's gonna be a binary. So put it this way: What if this is the next question, but I'll ask it now. What if the array I had was completely sorted?
So it's gonna be one
That's one line.
Yeah. So one line. All right. Do you guys see why?
because one is bigger than the other.
Yeah. And so we're always gonna be going. Well, if it's in increasing order, it's always gonna go down to the right.
Yeah.
Right, because all the numbers are going to be greater. Okay, does anyone not see that? That's like very important point. That if I give you an array with sorted numbers, insert it into a binary tree, that will look like just a straight line to your right. Okay? If you don't get it, make sure you spend some time on this and get it. And so the inverse of this question is, instead of being completely ordered, there's just the numbers are everywhere, completely random. I insert those numbers into my tree. What does it look like?
There's some likely to be a tree.
Well, it doesn't look like a straight line, obviously, because that's the extreme case.
What if the randomization of the output is that
Again, you're sort of trying to think about too specifically. On average, what do you think?
it will be branches?
Yeah, it should look like a tree, right? A complete tree, or a full tree in particular. Okay.
Wait,
This-
a full tree? Why is it complete?
I mean, it will look like it will look.
Why is it gonna be even, like, sort of like? It could be tilted in a way that one is bigger than the other. One side, left side.
Well, specifically for any particular case, but on average, it'll be full, right? Because then I'll have cases in which the other side is biased, then another case is biased, and altogether it'll even each other out. I'm sorry? No.
Alright, so it will be.
Well, averages are sort of you can't think of a specific situation when you talk about averages because it doesn't make sense. It's just you think about a bunch of different situations and then sort of weigh them equally to one another. Don't worry. So, anyways, going back to the question because we got off the beaten path here. So if the numbers we're inserting into the array or in random order, we'll get something that looks like a nice looking tree, right? The term actually is called balance, but we'll expand upon that later because that implies a bunch of other things. And so it just looks nice. It has branches on the left, branches on the right, and they're roughly the same size. Okay. Which a full tree satisfies, right? A full tree is balanced. And so the other question is if they're completely ordered, we'll get something that looks like a straight line, either to the left or to the right. Okay. So what's the big O of insertion for a binary search tree? N log n. Why?
Oh no, not n log n.
Log n. Why? Because
Because
that's.
you're going through.
Well, so if I don't insert at the root, where do I go?
Down
To the half, depending on where it's at.
Well, either left or right. You have a choice between two paths. So if I know it goes to the left, do I need to consider the right subtree at all? No. And so effectively, how much did I reduce my problem size by? Half. So I divide it in half. That says log base 2n. Okay, so log base 2n. And so I always have to think about it because I think I'm saying it wrong. Log base n2. But anyways, we know why, because we're cutting the space in half every time we find a place to insert. And so once we find the right spot, it's just constant time to actually do the insertion, right? Just create a node and just throw it there. Okay. So groovy, baby. What movie? Well, yeah, there's another one though too. Older. Bruce Campbell. Okay, never mind, you uncultured. Millennial, way before that. Do I look that young? I'm super old, dude. Anyways, if you don't know Bruce Campbell, then that's okay. No one's perfect. So, how do we find the minimum and maximum value of a binary search tree?
You go into the
Well, so which is which? If I go all the way to the left, what will I find?
The lowest one.
The minimum. If I go to the right, the highest one. Yep.
Oh, you're a Generation Z.
Am I? Okay. Maybe I could be older than that. Like I'm Asian after all. So here is the algorithm. Oh, actually, this is the implementation. Is this iterative or recursive?
Which one?
Both of them. The ones get min, ones get max.
There is.
Iterative. Well, how do I know it's not recursive?
You're not calling yourself.
Yeah, I'm not calling myself. I mean, it kind of looks recursive because it looks kind of nice, right? It looks kind of nice. But no, this is iterative. In particular, we see a while loop here. We're seeing a while loop, and we're doing some traversing with a while loop. Do not, if you want to use recursion, do not do this. Do not have loops that actually traverse your recursion. That's a good way to create very, very bad code. So, okay, iterative. That's the algorithm. You see, the min node is obtained by traversing left. Max node is found by traversing right. Easy peasy. Question mark. Okay. I state it that way, but I'm not sure. So what's the big O of finding the min or max? I heard it once. Do I hear it twice? Log 2n. Does anyone not see that? It is log 2n. Not see it. Okay, so we'll talk about it. So, yes, I like it when people ask questions like this. So, if I want to find a minimum of this tree, I know I just need to go left. If I go left, I no longer need to consider my right subtree. And so effectively, I cut my problem size in half. And I just keep on going left, and I cut my problem size in half. I go left, I cut my problem size in half. At some point, I'll get to it, if it's there. Well, I will. Once I hit the null, I know to stop, right? And so, boom, there. Right. So anytime you cut the problem size in half, it's log base something. Well, log base 2 in this case. If I cut the problem size in 3, it's log base 3. Same thing with the right. Right. Because at some point, I just no longer need to consider anything on my right subtree if I'm going left. And you can kind of count. Let me see if this ends up being nice. So 1, 2, 3, 4, 5, 6. No, it needs to be a bigger tree. But I mean, I'm only going 1, 2, 3 steps to find berry out of a tree that might have 6 nodes. So it's clearly less than n. But anyways, yeah. So that's that. Is that good? Okay. So boom. Actually, I sort of, you guys did not see that. Okay, I want to print this in alphabetical order. How do I do it? Well, I mean, well, so which node do I print first?
The one all the way to the left.
Okay, so I know I print this one first.
Oh yeah.
And so, well, let me ask it this way. We know we always begin at the root, right? And so, relative to the root, which subtree do I print completely first? The left, and then I print the root. Then I completely print the right subtree, right? Well, yeah, it's implied, right? So I'm assuming this is almost like a recursive thinking. So starting here, I first print my left subtree, then myself, and then my right subtree. And Jimmy said it, I didn't quite catch it. I mean, I don't know if you actually...
In order?
Yeah, so that's the traversal. Yeah, that's sort of saying I need to do things in order. Just
No.
Okay, so the traversal. Okay, so... But I don't think everyone else heard that. So for those who didn't hear it, did you guys catch what I said? All right, so what we're doing is we print the left subtree, myself, and then my right subtree. Which traversal is that? Where I... Well, post is print left, print right, then myself.
In order traversal.
Well, that's right, but pre would be print myself, then my left, then my right.
Yeah.
Okay.
Because you always print that one. Well, in that one.
Well, I mean, it's just, I print myself in the middle is essentially the one way to interpret it. But in terms of the way we solve it, we go left, process, go right. Right. And so it ends up being in order, but the name kind of gives it away anyways, other than the fact of telling you when you process. But yeah, so it ends up being in order. And so there it is. This might look familiar. All right, so I go left first, print myself, and go right. And so let's go ahead and do it. Boom. So Bill, Danny. Well, we print myself, and so what happens? Print right. And I think you guys get this. We actually went through a couple of these traversals last time, and so we're not drawing every single function call. Okay, so we at this point, relative to the root, we print everything within the left subtree. Okay, and then we go ahead and we'll print Jane. Boom. And then the right subtree relative to Jane, which just consists of Wah. That's a cool name. I don't know anyone named Wah. Do you guys know anyone named Wah? Wah. I mean, that's how I would call them. Wah, come over, have some pizza. Okay, and so, I mean, this is not a very balanced tree, but if it were completely balanced, what could you say about where Jane would reside within these lists of names? Say if I had 3 nodes here and 3 nodes here.
In the middle.
Yeah, it would always be in the middle. And so it's just sort of a way to reason about this in order traversal, that the root node will always be, well, in the middle if this was a balanced tree. But I mean, if I tell you that Jane is the root node, you know what nodes reside within the left subtree, right? Be everyone here. And then everyone after Jane would be in the right subtree. Okay? You might need to notice for an assignment coming up. Well, I'd have to tell you, right? So if I just gave you these lists of names and I wanted you to give me what's in the left subtree, I'd have to tell you where the root is. Right? So if I say Frank is the root, then you could say Bill and Danny are in the left subtree, whereas Jane and Wah would be in the right subtree. Okay. So that's how you print a binary search tree. What is the big O of printing a binary search tree? How many steps did we take? Well, how many nodes did we visit? All of them. And so a traversal will always visit all the nodes, and boom. Almost a trick question. Did anyone think log base 2n? Yeah, it's all right, so did I. But it's n because we visit every single node. Okay, so when we're done with our tree, we have to free every single node one at a time. Well, so this implies that if we want to delete every single node, that implies how many nodes we visit? N nodes. How do we visit them? Post order. Why?
Because if you go pre-order, the parent node is going to be the last two edges.
Yeah, that's a good. That's
You're the last right.
So if I do pre-order, who do I delete first? Jane. So what happened? Yeah, I just lost everyone else. I lost all my kids. That's what happens when you do a pre-order traversal. You lose your kids. So, well, anyways. But post order makes sense, right? Because I go left, left, left. I see if I have any kids to the left. I see if I have any kids to the right. No and no. What do I do? Kill myself, right? Well, the slides and the linked list. Oh no, you guys don't remember the linked list lecture. Okay, and so, boom, post order. Well, this is printing, so let's go ahead and so free tree. So base case, I first take a look down my left subtree. I take a look down my right subtree. If there's no one down there, I can go ahead and delete myself. So post order traversal. Pretty straightforward. Any questions on either printing a tree in order and or freeing a tree? Okay. And then you guys can step through this, but you guys get the point, right? Boom, get to the last node. There's no one to my left, no one to the right. Boom. Again, no one to my right, and then delete myself. Okay, dokie. So that's deleting. And I'll skip through this as you guys go through this process. And again, this is a traversal. We delete every single node, and so we have this. The order of this is order n. Okay, and so we don't want to delete every single node, but just a single element. Is that a quiet wait? Okay. So we want to, well, let me ask you, what happens if I want to delete Darren? Just Darren. I don't like Darren.
Move carry up top.
Move carry. Well, that's a good, well, so that's, if I wanted to remove Darren, there leaves a space that we need to fill, right? My life is empty. I need to put someone there. Now, it's almost Christmas too, so it's like a super sad season. Yeah, Ken. You're gonna say, Ken?
Delete Darren. There's just these random empty things in space memory.
Mm-hmm.
You're not gonna be able to connect them back. Right?
Oh yeah, yeah. So assuming that I had a way, yeah. So that's a good point, right? So I need a way to keep track of these guys.
Okay.
So I can't just do that. Assuming that we have that, that's a very good point. Assuming that we have actually something pointing here, we need to fill this void because right now it's just.
Well, you close the loop. It's like kind of like pushing Mel inside and then Rick up top.
Well, yeah, I could do that. That's one way to do it. Well, I guess the point is, are there different ways of doing this? Yes. So and we'll figure out how to do it. Exactly. Yeah. Okay. So we can relink in any number of ways. And so I can't do it. Well, I can't do it arbitrarily. There's many ways of doing it, but I can't just simply choose a node and throw it in there. In particular, why can't I do this? Doesn't make any sense based on the rules of binary search tree. Specifically, what does this violate? Alphabet. We've like devolved into single word statements. Alphabet. That's the answer for everything. I'm sorry?
What are you going to do with all the children nodes?
Well, at this point, we have to make an adjustment. I'm just sort of commenting on whether or not this is correct. Answer is no because of alphabet, as according to Ebony.
Binary search. Okay.
Okay, and so let's talk about this. It's not a very straightforward problem. And so this is not a valid binary search tree. So simply moving arbitrary values into various positions will not work. We have to be a little bit more clever about this. And so first we need to figure out how to get there. How do I want to talk about this? Let's go back to the linked list. If I wanted to remove a node from a linked list, where do I need to stop?
You have to go through all of
When
it.
you found it.
You have to move everything. Oh, wait. You have to reroute that one.
Well, that's part of it, but even before that, I need to. So, let me draw it out. So suppose this is my linked list. This is the only color I have. This might be hard to see in the back. Come on, is this okay? It's like green. That's the only one I have.
See it, but I think look at it.
Okay, yeah. Let me draw it maybe larger. So I have 1 node, 2 node, 3 nodes. Let's say 1, 3, 4. If I want to delete this 3, and I have a head pointer too, right? So here's my head pointer. And so I start here, and I want to delete 3. If I traverse down to 3, can I simply delete 3? No. Right? Because if I just simply delete 3 and my pointer points here, I have no way to relink things because I've lost.
Professor, do you want markers?
Oh, you have markers? You are a lifesaver. Why do you have markers? That's awesome.
Do you need them? Yeah.
That's how you make friends with teachers.
Just carry around markers and you're instantly in their good books. Okay, so 1, yeah, that's much better. Thank you.
I can see now.
Well, so can I. I couldn't see it earlier. So, okay, and then this goes to null pointer. Right. And so if I want, my goal is to delete 2. I start here, and if I traverse all the way down to 2, and I try to delete 2, I would have lost. There's no way for me to connect 1 to 3 because I don't have 1 anymore. And so what does that imply about where I need to stop?
Why traverse at all in this example?
Well, I mean, assuming I have nodes, you can assume I have nodes before this.
Well, then stop
That's the whole thing, but in a general statement, where do I stop?
The one before the one.
Yeah, so if I want to delete a node with a linked list, I need to stop before the node I want to delete. Okay. And so we need to do roughly the same thing with trees. I mean, we could solve this problem by having, well, this problem could have been solved if I had a previous pointer, right? I could have traversed down to 2 and gotten back, but we're lazy, so we're going to keep it easy. And so the problem would be solved in the case of trees if I had a, well, yes, my wand, thank you. So it would be solved if I had a parent pointer in my node definition. You guys understand why that's the case? Because if I have a parent pointer, I can just go back. Find a node I want to delete, go to my parent, and relink from there. Okay, does that make sense? But we don't have parent pointers, so that solution is out the window. So what we do instead with trees is that we use 2 pointers to traverse. Okay, just like with this, I could have used 2 pointers, but we don't because it's a simple structure. I could have a pointer that starts here and here. If I wanted to delete this 3, say, and this points to other nodes, I would simply move this node here, and this pointer here, and I can delete 3, but I already have a node to 2, or a pointer pointing to 2, right? We could do that with linked lists, we just don't because it's not necessary, right? We can always just check the next pointer. But that's what we do with binary trees.
Wait, you move the 2 back?
No. I mean,
Anything before 1?
I don't move anything. I just have 2 pointers traversing my list instead.
Oh, you're saying just to traverse it, not to delete it.
Well, not yet. So if I have, well, again, if we, just in contrast to what we had previously, if I only choose to use 1 pointer for this deletion algorithm, I have to stop. If this is the node I want to delete, I have to stop at the node prior to this.
Right.
But if I chose to use an algorithm that carried around 2 pointers, like say 1 here and another one that traversed, and they just traverse together through the tree, I can stop the picture here because I have pointers to both the previous node and the node I want to delete.
Oh, okay.
Okay. But this is the tactic we're going to employ with the binary tree, right? Because we need to traverse down the tree to find a node we want to delete. But again, generally speaking, if you only have 1 pointer, we need to stop at the node before the node we want to delete, right? But that has some issues with it. And so that we get around those issues, we're using 2 pointers to traverse down a tree. And so as we're going down, we'll always have access to the parent node. That way we can delete the node we want to delete and relink things in some fashion. And so given a value v we want to delete from the tree, we find the value in the tree with a slightly modified search. We use 2 pointers, a current pointer and a parent pointer, right? So there's the 2 pointers. Boom. If the node was found, delete it from the tree, making sure we preserve its ordering. This is kind of vague. We'll define what this means. And there are 3 cases in which we can preserve the ordering. Okay, so here's the first part of the algorithm. This is just looking for the value, right? So we have 2 pointers, one in which will point to the parent of a node, and a current pointer, which is what we had previously for binary search, right? And so while the current node is not null, we simply ask, is the node that we're looking for the current node? If so, then we're done. Otherwise, if it's less than the current value, we go which direction? If v is less than the current value. There's 2 ways in which you can go. To the left, right? And so what we do is we just move our pointers up. So this takes the place of where current was pointing, and this goes down to the left subtree. Otherwise, we do the same thing on the right. Okay? Any questions on this? This is just searching. But this is identical to the binary search tree algorithm that we talked about earlier. The only thing that's different is the addition of this parent pointer. But we talked about why we use this, right? And so everything's identical other than having a parent pointer. When we're done with our loop, we want the parent pointer to point to the node just above the node we're trying to delete, right? That way we can relink things. And so if we want to delete Arisa, we want our parent pointer to point to carry. Okay? Does that not make sense to anyone? We see that we want to delete Arissa.
Yeah.
And so where should the parent pointer point to? Well, we want to delete this, right? So we can't have our pointer point here because we can't relink things.
Yeah.
And so where should we point to? Carry. That's it. That's all I said. So now that's just looking, that's what we're searching, right? So let's go ahead and delete Casey. And so, I mean, the picture should be what? So Casey's the person we're deleting. And so we'll traverse down to Casey, but I also have a parent pointer who points to carry. Okay, so let's see how we arrive at that situation. And so we have a cur pointer that points to Mel, while cur is not null. And so clearly cur is not null because cur is pointing to Mel. Is Casey equal to Mel? No. No. And so we ask the question, is Casey less than Mel? Yes. CM, yes. And so what do? We move this to point to whom? To cur, who is pointing to Mel, and then we just have cur traverse Darren, who is left to Mel. Okay, this is just binary search, just with 2 pointers. And so boom, and boom, and now the picture looks like this. We start back up to the top of the for loop, or while loop, whichever. And so is cur, which is pointing to Darren, is that the same thing as Mel? Or, no, I'm sorry, Casey. No. Is Casey less than Darren? Yes. CD, yeah, so CD. And so we move parent up 1, we move cur which direction? To the left. Boom. And so we do this problem one more time. We ask, is carry the same as Casey? No. Despite, well, off by 1 letter, but still. No. Now, which direction do we go from carry? Right. To the right. And so we want parent to move up here, cur to move down here. And so parent points to carry, cur goes right. We go back to the top of the while loop. We ask, is Casey equal to Casey? Yes. Boom. And so we're in a situation now where we can delete Casey. Okay? Because we have something pointing here, which allows us to relink, and then this can get deleted once we handle things. Okay. So this whole process was simply to get to the point where we can relink things. Okay. Any questions on this? Yes.
Casey has a left child in case. Then you try to delete Casey.
Casey, just saying that we have a situation where Casey would have a left child?
Yeah. Or 2 children.
Oh yeah, so 2 children? Well, we'd have to handle that differently. But we'll see those situations. We'll see all, there's 3 situations, we'll see all 3. Well, the 3 situations are 1 child, 2 children, and no children. Okay. Now, once we found our target node, and we have a pointer to the node previous to that which we want to delete, we need to examine 3 cases in which the thing we want to delete is a leaf, boom, boom, no children, a case in which the node we want to delete has 1 child, in this case Rick and Pauline, and then the final one in which there are 2 children after the node we wish to delete. And let's go through each one. Okay, so first case. Target node is a leaf. Although let's actually break here because this is actually important and it's a little difficult to follow. We've been talking about algorithms for a while now, so take 10 minutes and we'll come back fresh to look at this. Yeah. Question just. Okay. Well, yeah. So break. 1, 2, 3. Yeah. Cool.
So if maps is using the binary tree, but if the objects you inserting is not here, it's the object type.
How old are you?
you'd have to define a comparator for it.
Yeah.
You'd have to overload the comparison operators.
So they,
Yeah.
but when you, but what about, but there are different kinds of maps, right?
Yeah, there's two maps. There's different implementations, which is kind of what you're talking about, but then there's also different kind of maps. In STL, there's what's called the map, which you already know, which is based off a binary search tree, and then there's what's called an unordered map.
So on order will be less efficient in a sense that.
No, well, it depends on what you mean in terms of efficiency. Now,
Like say, say you wanna rotate one node, and since the map is not
It-
ordered, how you know?
it depends. Well, so if for you as a user, your primary concern is printing things in order, don't use a hash table or don't use an unordered map. Use a binary search tree map, right? Because that's what's important to you. Now, if you don't care about the order of these things, like say phone numbers, maybe you don't care about storing phone numbers, but you want to be able to get these values quickly, the unordered map might be a better idea.
Are we gonna reach the hash map?
Yeah, that's actually the next thing.
Okay.
Yeah, well, we'll talk about this again.